Here we go, looking at 4.1, connecting the dots, piggies and pools. So, my little sister Savannah is 3 years old. She has a piggy bank that she wants to fill. She started with 5 pennies, and each day when I come home from school, she's excited when I give her 3 pennies that are left over from my lunch money. Create a mathematical model for the number of pennies in the piggy bank on day n. So, that first thing, we want a model. Okay, so what kind of models do we have? Well, we've got tables. Picture/diagram, graphs, equations, right? We've got all of those, recursive and explicit equations. So those are the main ones we like to deal with. And it wants to find day n, so it tells us that one of these models is going to help us understand no matter what day we decide to stop on. So I always like to start with a table. I think it's easiest to get going. So what do we have here? Well, we've got days, right? And we have number of pennies. So when she started, she had 5 pennies. Then the next day, when I gave her 3, we added 3 to that, and we had 8. Then day 2, we had 11. Day 3, 14, and so on, right? So that helps us understand it, but it doesn't necessarily help us with this day n. Day n, because we'd have to keep writing the table to find it. So maybe something else would help us with that. Maybe an equation. Okay. So remember, if we're going recursive equation, it's always f of x. And actually we're using n, so I should probably make that f of n. F of n equals f of n minus 1. And we are adding 3 pennies a day. And we started out with 5 pennies. If we're going with the explicit, we just go f of n or y equals, well, we started with 5 pennies, we're adding 3 every day, so we times it by that. Which is a great one to help us, with this n. We could also make a graph, right? Now, there's a few things to note when we're dealing with a graph. When we are graphing from a story problem, there's a few things we have to pay attention to. One of them is our domain. In other words, what are the possibilities here? Well, we started at 0, 5, right? Okay. Can I go back to a negative day? No, because we started with 5. That's where we started. So it doesn't make sense in our problem to go back, even though it would make sense just looking at our equation. So on day 1, we went up to 8, right? Day 2, we went up to 11, and so on and so forth. Okay, something like that. But it doesn't make sense to have it go down this way. Okay, there's another aspect, so its domain would be from 0 to these positive days, right? That's what its domain would be. Okay, those positive, from 0 to those positives. So that's important to pay attention to. The second thing is we need to distinguish between these two important parts of a function, discrete or continuous. If something is discrete, it grows in pieces. If something is continuous, it constantly is growing. So what do we mean by that? Well, the graph's the easiest one to see. Okay, should I connect the dots? Okay, if I connect them, it's continuous. If I don't, it's discrete. Well, think about the problem. What is the problem telling us? Look, she's getting 3 pennies every day, right? Now, if we're looking at this, this stands for 1 penny, 2 pennies, 3 pennies. Okay, this stands for a day. As I'm going throughout my day, is she earning a penny at half the day or at a third of the day? She isn't. If I were to draw a line, though, that's what I'm saying. I'm saying if I went up to this point right here, after a third of the day had gone by, she would have earned a penny. But is that true? No, she only got the pennies every end of the day, okay, when that next end of the school day appeared. So really, there's nothing going on in between here. Okay, we don't get it until that full day arrives, then we get the 3 pennies. That next full day, we get the 3 pennies. That next full day, we get the 3 pennies. So we should leave the line with just the dots. Okay, that would be discrete because it's growing in pieces. The only way you could fix that was if you had a 3D printer and you were, building pennies, so you're constantly building those pennies. That's the only way it would work. But this one would be discrete, so we should leave it without the lines for that model. Now let's take a look at the next one to help us understand continuous. So, our family has a small pool for relaxing in the summer that holds 1,500 gallons of water. I decided to fill the pool for the summer. When I had 5 gallons of water in the pool, I decided that I didn't want to stand outside and watch the pool fill, so I had to figure out how long it would take so that I could leave, but come back to turn off the water at the right time. I checked the flow on the hose and found that it was filling the pool at a rate of 2 gallons every minute. Create a mathematical model for the number of gallons of water in a pool at t minutes. So we've got minutes, right? T, time. And then we've got water in the pool. So we started out and we'd already had 5 gallons in there, right? When we started timing. After the first minute, we had 2 more gallons. So we had 7. The next minute we had 9. The next minute we had 11, and so on. Okay? So if we were making an equation, we would have f of n equals f of n minus 1 plus 2, and f of 0 equals 5. That's our recursive. Our explicit would be y equals started at 5, added 2 multiple times. Oh, t, not n, right? Dealing with t here. Guess that should be f of t and t minus 1. Okay, what if we graph it? So at 0, 5, that's where we started. Now once again, thinking about that domain. Does it make sense to go back in negative minutes? No, it doesn't. Or negative water? No. So we start at 0. That's the start, those positives, okay? From 0. But how far is it going to go to? How many minutes until we'd fill it up? Am I going to fill it up more than 1,500 gallons? No. So my domain would go to wherever that pool is full. That section would be it. So it's not going to continue on forever. But if we keep graphing it, it would look something like this, right? Now, should we draw a line here? Well, think about a pool. How is a pool going to be filled up? Okay, well, you've got the hose, and how does water come out of a hose? It comes out continuously. So, if I stopped at half a minute, would I have more water than at my minute? I would. That's what we mean by continuous. Okay, that's when we would draw the line. Because this water is continuously coming out to fill it up. I stop it at any time, and it's going to have a different amount. Whereas, if we thought back to the pennies, if us, I guess it's us, right? Because we say my little sister. But whoever's talking here, if they died before they took lunch and got those 3 pennies, we wouldn't have any growth whatsoever. Here, if the hose got cut off and stopped filling it up anywhere along this line, we would still have a different amount. Okay, so when you think continuous, think like this hose. It's constantly going. Okay, now, if we wanted to think about this in a discrete manner, we'd have to fill up our pool with buckets, right? And that's a squarish bucket. Because then all the chunk of water would go in at the same time, then I'd have to walk back, get more water, and throw it in. Okay? So, thinking about these, let's take a look at problem number 6. It wants us to compare problem 1 and 2. Do we see some similarities? Well, they're both growing by addition, so they're arithmetic, right? They both make kind of straight lines on their graphs, even though one's just dotted and the other one isn't. Okay? So, another similarity, they're straight lines. Okay, their equations look pretty similar. What differences did we notice? Well, one was discrete, one was continuous. Okay, that was a big difference we noticed there, right? Okay, any other differences? Well, one grew at a different rate, right? Different rates. Oh, they also had the same starting, the same y-intercept, right? The same starting number, but the different growth rates. Okay, I think that's good enough. So let's take a look at problem 3 and 4, and we'll come back to number 7. Okay, so 3. I'm more sophisticated than my little sister, so I save my money in a bank account that pays me 3% interest on the money in the account at the end of each month. If I take my money out before the end of the month, I don't earn any interest for the month. I started the account with $50 that I got for my birthday. So let's start with the table. Okay, so we have months, and we have money. So we started out with $50 he got for his birthday. Then after the first month, he earns 3% interest. Okay, so what are we doing? Well, to earn interest means you take the full amount, the 100%, and you add to that the 3%, right? So we're making 103% of our original. Now, we don't just add that 103%, we have to multiply it by the 50. So we turn it into a decimal, so it would be 1.03. That's what we're multiplying by each time. Okay, 1.03. So if I get out my calculator and I multiply 50 by 1.03, we get $51.5. Second month, I do the same thing, times it by 1.03. So I get $53.05 if I round money-wise. For 3, if we keep going, $54.64, and so on. Okay, could we make an equation here? Yeah. So where did we start out? We started out at $50 times it by 1.03 multiple times. That's what it would look like. Oh, f of m. Forget that they wanted the m, didn't they? If I did recursive, f of m equals f of m minus 1 times 1.03, and f of 0 would equal 50. Now if I graphed that, okay, this graph isn't very good, is it? So I'm going to kind of slightly adjust it. We're going to call this our x. This is going to be our x-axis. Okay. So let's see. We started out at 50, so let's count by 50s. 50, 100, 150, 200, so on. So at 0 we're at 50. We'll call 1, 2, 3. After 1 month, we were barely above that, right? Next month, barely above that. And maybe I need to count by less than 50. Right? And so on. So it's getting bigger and bigger. What's eventually it's gonna look like would be like this. But the problem is it discrete or is it continuous? Well, if I take my money out before the end of the month, I don't earn any interest. So halfway in here, he didn't earn anything. Halfway in here, he didn't earn anything. So nothing's in between, which would make it discrete. So it would look eventually like that. You know, over many, many months. It would take like 25 months before he cracked $100. So it's growing very, very slowly, much slower than my graph would show. But eventually, if we zoomed out, it would look like that. But it would be the dots, because it's a discrete geometric function. Okay, let's take a look at 4. At the end of summer, I decided to drain a swimming pool. Okay, notice that it drains faster when there is more water in the pool. That was interesting to me, so I decided to measure the rate at which it drains. I found that it was draining at a rate of 3% every minute. Okay, so how much did we start out with? Well, look at our pool, 1,500 gallons. When we started draining it, and it's draining at a rate of 3% every minute. Okay, so if we've got a full percent, we're subtracting 3% every minute. So T for time in minutes. but we're draining by 3%, so we're left with 97%. So we would times by 0.97. That's how we'd get the next number. So 1,500 times 0.97 gives us 1,455. Then 1,411.35. Then 1369.009 and 1327.94 and so on. Okay, so this one we would actually start up really high on our graph. Now, is it continuously draining? Yeah. Okay, just like we fill it up continuously, it drains continuously. We're not taking a bucket and emptying it out. So it's a continuous geometric function. If I made an equation, it would be f of t equals f of t minus 1 times 0.97, and f of 0 would equal 1,500. We would, for explicit, f of t equals 1,500 times 0.97 to the t. So it would start at 1,500 and it would slowly be going down like this till we got empty. But because it's continuous, I would draw my line like that. And it would look something like this. Okay, which is, didn't really want to focus too much on the graph other than seeing that difference between continuous and discrete. So if we compare problems 3 and 4, their similarities, they're both geometric. Okay, their equations are similar. Did they have the same y-intercept? Nope. Did they have the same growth rate? Kind of, except one was going up by 3%, one was going down by 3%. So they were growing by 3%, just in different directions. Okay, they kind of had a curved line. Okay, what was different? Well, their y-intercepts were different. They started at a different place. One was discrete, one was continuous. Okay, so those are kind of those main differences. Now, look back at number 5, problems 1 and 3. Well, 3 was discrete, same way with 1. So they were both discrete. That was a similarity. Anything else? Okay, differences. Well, one was arithmetic, one was geometric. So their lines were different. Their equations were different. Their y-intercepts were different. Okay, there was a lot of differences there. And some similarities. But there's the main idea there. So understanding the difference between discrete and continuous, how that affects the line, how you draw it, and what makes sense, pretty important.